So first, let me thank the organizer for inviting me to this conference. So I'm going to talk about a different kind of gravitational wave from what Shubhendra has discussed in his talk. So I'm going to talk about the stochastic gravitational waves. And this comes from the electroweak phase transitions in the early universe. So let's move on to the outline of the talk. So I will very quickly go through some basics about Higgs boson and electric symmetry breaking and how electric phase transition in the early universe can be connected to baryon asymmetry in the universe. And finally, unfortunately, electric symmetry breaking and cannot be strong first order, and hence baryon asymmetry, electric baryogenesis cannot happen within the standard model. So we have to go into the beyond the standard model paradigm. So I will talk about a very simple extension of the standard model. And finally, how from strong first order phase transition gravitational waves can be generated, and connection of this parameter space with the Higgs searches at the LHC. So this is a complementarity between the gravitational wave experiments and the high luminosity run of the LHC. So both of them, high luminosity LHC is going to run for another 10 years, and LISA, which is going to probe this electric phase transition, that temperature scale, that is going to be online in 10 years time. So if we are lucky, we may get some correlation there. Okay, so I presume that you are well versed in the Higgs mechanism. If you're not, then we can discuss later on. But I will just quickly go through. This is the typical periodic table for the standard model of particle physics with all the leptons and quarks and the force carrier gauge bosons. However, in a gauge theory, you have gauge invariant theory, you have these gauge bosons to be massless, which are in conflict with the W and Z boson masses measured at LEP. So, so this is we need to bring in something to explain the masses of the heavy masses of W and Z boson. So for that purpose, Higgs mechanism was proposed. So if you have a scalar doublet, SU2 doublet, which is a complex scalar field, and if you write this scalar potential with mu square less than 0, then you get this kind of Mexican hat-like potential where when the field is here at the field value 0, all the gauge bosons are massless, and it rolls down the potential, and you get a non-zero vacuum expectation value, which in other words called wave, and then all the standard model particles become massive. So finally, in 2012, which is almost about 50 years after Higgs boson was predicted, LHC discovered the Higgs boson, both CMS and ATLAS experiments, in Higgs to gamma channel. So Higgs decaying to pair of photons, where it was discovered. And this is the current status of Higgs physics in a nutshell, that if you compare its coupling with various gauge bosons and standard model fermions, some of the channels, the error bars are large, but more or less within 1 sigma, they agree with the standard model prediction. However, there are few channels that will remain beyond, like some of the Ikawa couplings that will be beyond LHC's. LHC will not be able to determine them. For example, with electron, which is too low, the coupling, and for the light quarks, the QCD background is so much that you won't be able to extract the signal. Then there is one very important coupling that is left, that is the Higgs self-coupling. So if you go back to the Higgs potential, so this lambda, that gives you the Higgs self-coupling. So easiest, so if one of the Higgs field gets a wave, and then you have a cubic coupling here, so that's why it's called a trilinear coupling. The best way, the one way to measure that is by Di-Higgs production at the LHC. So why do we need to measure this coupling? So this is very important, and for, yeah.
So can we ever measure this electron coupling with the Higgs in FCC?
FCC?
Yes, say for example.
FCC, I don't bother too much. It will be too far.
No, but suppose then I'm a very like
optimistic.
No, pessimistic person. Then how do I ever say that I have discovered Higgs?
Huh?
So how do I ever say that I have discovered the Higgs boson? I always say that I've always discovered a Higgs-like boson. Can I ever say that I have discovered the Higgs boson? The question I've asked many people. I don't know if there's an answer to that or not.
Well, I mean,
also the quark couplings, as you said, the light.
So there is still a possibility that Higgs can be composite in like coset theories. Like coset group theories, and there will be correlation between, say, for example, HWW and HHWW. If we can measure those couplings very precisely, then one can perhaps distinguish between various propositions of Higgs bosons. And so two of the main cases which are still there, but that is very unlikely that we'll be able to measure that with that precision. With LHC, we cannot do anything.
So LHC will always say we have measured a Higgs-like boson.
Of course, they always say Higgs-like boson.
Okay.
So even lambda is not measured. So we don't know the full story of the electric symmetry breaking there. Okay. We only know that Higgs couples to W and Z, so it has some connection with electric symmetry breaking. That is all we can say.
Okay, thanks.
May I add one comment?
Yeah.
I mean, I think measurement of lambda to a large degree will confirm that we have the Higgs boson, to be honest.
Yeah, I would agree with you, but
No, because that is a very characteristic thing of that Higgs potential.
Yeah.
And that would be something that it's a prediction of standard model without the matter sector. Because after all, the Higgs is for the electroweak gate sector. Yukawa couplings are anyway put in by hand. That is not. That is the extra parameters that are put in by hand. But this tests a coupling that results from the behavior of the Higgs potential and the gates couplings, gate sector only.
Yeah, I would agree with that. I was actually coming to that somewhat in the same kind of arguments, and so this thing is so just continuing on the discussion that we need to measure this lambda to understand this shape of the electric potential, and then we will have the full picture about electric symmetry breaking. However, if we have some additional scalars in the model in our nature, then this so in particularly in standard model you get a very nice relation between the trilinear Higgs coupling, which is lambda times the vacuum expectation value of the Higgs boson. So we know this V, which is connected to the Higgs mass. So this gets spoiled if you have extra scalar, and this extra scalar can decay to a pair of Higgs bosons. So that is we have to take in that I am going to talk about more in this rest of the talk. And also understanding this lambda, as Rohini already mentioned, we can understand the nature of the electric, symmetry breaking. But on top of that, also we can understand the stability of the vacuum, electroweak vacuum. Currently, with the measured Higgs boson mass and top mass, it is metastable at best. And also electroweak phase transition in the early universe, that is what we can have some idea about that. Electroweak phase transition is connected to the generation of baryon asymmetry in the early universe via baryogenesis. Okay, so how we can measure this trilinear coupling lambda? So this is the how we produce pair of Higgs in the at the LHC. So you get this kind of like a S-channel exchange of a off-shell Higgs, and then two on-shell Higgs come out of that. And also you have this box diagram. And these two diagrams, they interfere destructively. And this is non-resonant Di-Higgs production, which can measure your this coupling lambda, or rather it is something like some factor times lambda times V. So yeah.
The mass of the heavier boson, like
so I will get into less than T, few hundred GeV. Yeah.
Maybe I'm missing something. Where is the lambda in the second diagram? So you're assuming that those Higgs are again decaying.
No, in the collider, all the diagrams will contribute. So here we are assuming all the couplings are known. Yeah, interfering with that. And this is a destructive interference. So if you, this is the top plot is the production cross section. If you, this lambda over lambda standard model, if you vary this number by some scale factor, you will see for standard model case, the cross section is quite low. And if you increase it a bit more, then around this ratio of 2.5, this cross section reaches this minimum. At this point, I would say people are trying hard to measure this Di-Higgs, see this Di-Higgs channel and measure lambda, but prospects are not great at this point. For Di-Higgs production, cross-section is about only 30 femtobarn, assuming standard model-like coupling, which is 3 orders of magnitude less than the single Higgs production, which we have already discovered. Okay. So, however, if you have this is the non-resonant part, but instead, if you replace this small h by some heavier scalar, then it can decay to a pair of Higgs boson, and if the decay branching ratio is high enough, then you get a resonance here, and you can see a significant enhancement in the cross section, but then you cannot say that you have measured lambda. So that is called the resonant Di-Higgs production. So moving on to baryon asymmetry, basics of that. So we know this like Dirac equation, or in quantum field theory, we have seen that between the fermions, there is no discrimination between the particle and antiparticle. However, we see this eta ratio from BBN and CMB, which is a very small number. And if you take an inverse of that, number density of antibaryon is very small. For practically, you can take it to be 0. So this means that for about 10 to the power 9 pairs of baryon antibaryon or E plus E minus, you get 1 extra baryon. So that is the amount of asymmetry that was created in the early universe, and that small asymmetry is responsible for everything from small large scale structure to all the visible matter to possibly dark matter also in the universe. So now the question is, our quantum field theory did not teach us how you can create this asymmetry. So we have to figure out a process like how to do that. So that was proposed by Sakharov in 1967. So assuming there is a CPT conservation, so these are the 3 criteria. First, you have to have some kind of baryon number violation in your model or Lagrangian, then charge conjugation and charge conjugation times parity violation, and finally loss of thermal equilibrium. But since my focus is mostly on the gravitational waves production, so I will pay attention to the last part of the this condition, third condition only. So I am presuming that there is some mechanism in the model by which I can generate baryon number violation, and also I can do CP violation there. So loss of thermal equilibrium is needed because even if you create your baryon number violation or CP violation in the model, but still when you are in thermal equilibrium, the distributions for the particle and antiparticle would be the same, and any asymmetry will be wiped out when everything comes into thermal equilibrium. So we need to create a situation where out of equilibrium is needed. So some popular models of baryogenesis, electroweak baryogenesis, leptogenesis, and so on and so forth. These 2 are particularly testable in the laboratory, and I am going to focus only on the electroweak baryogenesis. So this is a cartoon or schematic diagram how electroweak baryogenesis can happen in the early universe. Say, for example, so we have let's go back a bit. So we have seen this Higgs potential. So now when we go to the early universe, there will be thermal correction to that. I will show the shape of the potential soon. So this is like the shape of the potential. So in case if you have so now this is a false vacuum at very high temperature, electroweak symmetry is restored, and you have this phi equal to 0 as the false vacuum. And then at some temperature when the the true vacuum, which is like wave not equal to about 246 GeV for standard model, that starts developing. And so in the plasma, you can think of it's just like bubbles in like when water is boiling. So in the plasma of the unbroken phase, which is when the electroweak symmetry breaking is restored, you start creating small bubbles of the broken phase. That means where the wave is non-zero. And then by say some mechanism, we create baryon lepton number violation, and then So I'm not going to talk about Phaleron much, but there is something called electroweak Phaleron process, which can convert lepton number violation to baryon number violation, and we create this baryon asymmetry. And then this small bubble of the broken phase which was created, it starts expanding, and it will catch this excess baryons. However, we have to make sure that the reverse process, the reverse Phaleron process, that can again dilute this additional baryon that has been created, that is suppressed within this broken phase vacuum. And if we look at the Phaleron production rate, this is roughly goes like this: energy of the Phaleron by temperature, where energy of the Phaleron is proportional to the wave of the Higgs field. For sufficient quenching, like we can reduce this relation to this, like the expectation like wave at the nucleation temperature divided by the temperature itself greater than or equal to 1, where nucleation temperature is the temperature at which bubbles of critical size has been formed, so that it cannot collapse under surface tension, and so on and so forth. Now, coming back to the phase transition in the standard model, people have calculated standard model electric phase transition within standard model for a long time. Unfortunately, in the standard model, strong first order phase transition could have happened only if Higgs mass was in this range, 75 to 80 GeV. But we know Higgs mass is 125 GeV, so there is no first order phase transition in standard model. So this is typically again the evolution of the potential at with temperature. At very high temperature, you have electroweak symmetry restored. Then as you lower the temperature, there is this second minima starts developing. And at T equal to Tc, which is called the critical temperature, these two minima are degenerate. And then you have at temperature less than Tc, this true minima of the electroweak minima starts becoming the true, it is deeper minima. Okay, so now what we tried to see, if we extend standard model by the minimal degree of freedom, that means we add a real singlet scalar to the standard model, can we save electroweak symmetry breaking? I mean, this is known for some time. So this is on top of this Higgs doublet that you have in the standard model, we add a singlet scalar where you have this additional vacuum expectation value of the singlet scalar. Singlet means SU2 singlet. And then you have this full potential with some additional parameters, 1, 2, 3, about 5 more parameters. 2 of them can be replaced by the minimization condition, and then the physical Higgs states are mixing between the doublet and the singlet, and then replacing the some of the parameters by the physical mass and mixing angles. You are left with these 5 parameters, and B3 and A1 are the cubic couplings here. So there are many theoretical and phenomenological constraints on this model. Some of them are like boundedness of the potential from below, like electroweak vacuum has to be stable. So, and also we also imposed electroweak minima is the global one. So that is the global minima, not a local minima. And then also unitarity perturbativity of the all the 2-2 scattering processes is in the model. Then from the experimental side, Higgs. Because Higgs, this H1 is the 125 GeV Higgs that we have found, so which is a mixture of the doublet and singlet. So now this coupling of this Higgs with the standard model particle is modulated by this cosine theta term. So measurement of Higgs signal strength gives you a bound on this coupling. And so we took this bound from the 2016 study. It may have improved a bit, but that will not change things much. And also there are electroweak precision calculation, like the loop correction to like W mass and various other electroweak precision observables. And that gives you the strongest bound on this coupling, this mixing angle, which is about 0.2-ish, little bit above 0.2. Now setting that up, now how about the electric phase transition within this model, singlet extension of the standard model, real singlet, which is otherwise called XSM in the literature. So we need to calculate the thermal correction to the scalar potential, assuming mean field theory. So only thing you get if we just do this simple high gauge invariant high T expansion, you have this correction to the mass terms of the doublet and the singlet. And because there are 3-level cubic terms there that can create this kind of barrier in the potential. So this barrier separates the false vacuum to the true vacuum. So the field can tunnel from this point to this point, and that can create the strong first order phase transition. Again, as I showed, because the waves are different in these two cases, reverse Phaleron process can be suppressed. And people looked at this Phaleron process production and etc. within this model, and you see there are a lot of freedom in the parameter space. So this is the line we need for quenching of the reverse Phaleron process, and there are enough points above that so that we can achieve baryogenesis within this model in principle. So now there are certain electroic like observables that we have to calculate to calculate the gravitational wave energy spectrum. First is this transition rate between the two vacua. For this we need this minimize this action, 3-dimensional action. And for a single field one, you can do it analytically by bound solution. But for multi-field, it's not possible to do it analytically. So you have to resort to numerical one. So this is a well-known code that can do it for Cosmo transitions. Typically, what you need is that the probability of a single bubble to be nucleated within one horizon volume, and that probability is order 1, which translates to like S33 T over T about 140. That is the condition of nucleation of a bubble of the broken phase. And also you can add this additional condition, which is needed for quenching of the Phaleron process. On top of that, you need to know the time scale of the phase transition. So beta is the reverse of the time scale of the phase transition. Alpha is the energy released during the phase transition. So first term is just the difference in potential energy between the true vacuum and the false vacuum, and this is the entropy release. And then also you need the critical temperature, which I already discussed. So then as these bubbles are formed for broken phase in the plasma, then there will be many bubbles that will be formed, just like think of boiling of water. And then they will start coalescing, and then this will also generate some shock waves in the plasma. And these bubbles and shocks can collide, and that will leave sound waves in the plasma, long-standing sound waves. Also, magneto-hydrodynamic turbulence can happen. So simulation, this is done by David Ware. So this is kind of how it looks like. Eventually, our visible universe should be within this false vacuum, true vacuum completely. So as I mentioned, there are 3 sources for gravitational wave energy density from the first order phase transition, collision of the electroic bubbles, sound waves left behind in the plasma, and also the magneto-hydrodynamic turbulence. If the time scale if it is a very slow transition, phase transition, then the sound waves and the turbulence are much dominant compared to the collision of bubbles. We can effectively neglect this term. So this has been shown by this set of papers. However, there are various subtleties and conflict between electroic baryogenesis and generation of strong first order phase transition. So first one is this the bubble wall velocity. So the energy amplitude of the gravitational wave energy depends, I mean, is proportional to some power of VW. I think you're very right. So yeah, so 1 over VW. Sorry, this is the VW here. So it's proportional to VW. So we need higher wall velocity to create enough amplitude so that it can be detected in interferometers. On the other hand, if VW is too large, then that will not give you efficient electroic baryogenesis. For that, we need very small velocity of the wall. So that has been resolved by looking at the velocity profile of this shock front. I mean, when this bubble is moving in the plasma, there is a shock front that is moving. And looking at the relative velocities of the plasma inside and outside the bubble, you have to take all this into account. You have to calculate from the conservation of energy momentum tensor, you have to calculate the velocity profile of the plasma, and that will help you solve this problem. So if we go to the, if this is in the universe frame, and if you go to the wall frame, you get this V plus, which is the plasma outside the bubble approaching this bubble wall. And this V plus that is actually enter into the electroweak baryogenesis calculation, and which we assume to be 0.05 that is needed for successful electroweak baryogenesis. So again, since we know the velocity profile of the plasma outside and inside the bubble, and also if you know this alpha, which is the amount of energy released, then you can calculate VW from solving those differential equations. So this is typically numerically how it shows. So what we did, we set V plus to be 0.05, and from this differential equation, we can calculate VW given we know the alpha, which is determined by the microscopic physics. So there are three modes of motion is possible within the plasma. There is something called detonation, which is where the plasma outside is static and inside flows outward. It is not, since outside is static, electroweak baryogenesis is not possible. Deflagration, and there is something called hybrid. So in deflagration, outside flows outward also, but inside static. In hybrid, both plasma, both inside and outside the bubble, they flow outward. So this is just the formula that you get from this set of papers where they did simulation to find these empirical formulas. Given that you know your alpha, beta, and VW, you can calculate the energy spectrum both from the sound wave and from the magnetohydrodynamic turbulence. Once you have this total energy density, you can integrate over frequency and then some running of this experiment. We consider that it's 5 years, and you calculate signal to noise ratio. And these are the, this is a bit old, but still this is mostly the set of gravitational wave experiment that is going to happen. So this is LIGO, typically LIGO range, and this is LISA. And electroweak symmetry, like phase transition, sits in around this region. However, it would be even better for if we have DECIGO, but that I don't know whether it will happen or not. So LISA is the only thing we can use to probe electroweak phase transition in the early universe at this point. So LISA, it will be like 3 satellites that will be placed in space with like distances of 10 to the 6 kilometer, and you will have I mean there are 3 interferometers there, and you need multiple interferometers to cross correlate and then calculate, I mean then get rid of the noise. And there are for 2 configurations of LISA, the thresholds are considered to be 10 and 50 respectively. Okay, so now let us look at some of the results and understand what physics is, what is needed like for a strong gravitational wave production. So we fix this sin theta, that is the mixing between the heavy Higgs and the light Higgs, to be 0.2. For other values of sin theta, the same pattern repeats. So one thing we need, if we here we plot the height of the barrier potential and the barrier potential, and here the distance between the 2 minima. So here we have strong signal to noise ratio which can be detected at LISA. So we need a relatively shallow barrier and deep minima, electroweak minima. And SNR is proportional to alpha to the 3 to the power 2. So same pattern basically follows. However, for beta, as I mentioned, the longer the phase transition, more gravitational wave energy density you can create, or amplitude is higher. So then you have like this is the region where you have large gravitational wave production, where your beta is like very I mean so this is the range where you have large gravitational wave production, where the beta is very small. So it's beta is the inverse of the time, so your phase transition is a bit longer. This is just details about, so you need large alpha and small beta to have a detectable gravitational wave at LISA. However, there are a few points here you will say that which has large alpha and small beta, which are have very low signal to noise ratio. That is because they are falling outside the frequency range of LISA, sensitivity range of LISA. And if we look at some other parameters like the wave of the singlet, so this is we found that a wave is allowed in a very small range. So this around 0, it is ruled out by the stability of the vacuum at t equal to 0, electroweak vacuum. At the higher scale, probably it is not allowed because whatever we are gaining by adding this extra scalar, which is interacting dynamically with the standard model Higgs, that dynamism that goes away, and a small value of wave is only allowed to have a successful, strong gravitational wave signal. So these other points I am ignoring because these are two-step phase transition. All I am going to discuss is one-step phase transition. If you are interested, we can talk about two-step phase transition in the discussion session. So typically wave range is allowed is 27 to 45 GeV for sin theta equal to 0.2. So this I'm showing for all kind of sin theta. So now, having said all that, so I said that we need to measure lambda, or we need to have some resonant Di-Higgs to understand the electroweak symmetry breaking or electroweak phase transition in the early universe. What we found is this, if we put this SNR ratio, like there are two configuration I told you about, 10 and 50, there is not much difference in the shape. In the heavy Higgs decay branching ratio to Di-Higgs, there is a sharp dip here. And that is typically in the collider jargon called blind spot. And you have to also take into consideration for detectability, you have to multiply this by the cross section, which falls with the mass. So it's even worse than what we are seeing here. And if we, this branching ratio is small, if the coupling of the H2 to pair of H1 is 0. Here we plot, this is the blue, pink points are all pheno and theoretically allowed points. Then the purple are like where nucleation of electroweak bubbles, true minima is possible. And then this green and red are the where detectable signal is possible. So you see that this is all points are clustered around this line where G211 is 0, and it changes with a very slow slope, low slope. So most of the points have a very low H2 going to H1 rate. And we found at least 56% points which has a branching ratio less than 1%. So it is already very bad. And this range, it is almost 100%, around 800 GeV. Now, if we look at the expression of, okay, so just a couple of slides. So this G211, you have this relationship where you have this cubic coupling for fixed sin theta, which we already fixed, and then Vs we see it varies within a very small region. So given you have G211 equal to 0, you can predict your G11 also. And we find that again, this is also falls in a region which is about 1.67. As I showed initially, that as you go towards this ratio of standard model trilinear coupling of Higgs divided by the standard model value, as that ratio goes towards 2.5, this cross section hits a trough. So this is again very small, and again this will also remain outside the high luminosity LHC run. So just a few words, what is happening here, why we have this narrow band. We picked one of these blind spot points and then keep all the parameters same and change the mass only and trace the phase histories of these particles. And these black points are where the nucleation is possible. So we take this plot into this same plane G211 to MH2. So this pink point is one of the blind spot points we took. And you see that as you go from left to right, your SNR increases. And so at this point, this is one of the blind spot points. And then after a while, you get these green points where you don't have any signal. So why that is happening? If we look at the alpha beta plane, so alpha is of course increasing as you approaching this purple point, but beta is going lower and lower. So what is happening? Slow PT is good for enhancement of gravitational wave, but if it is too slow, then if you go back to the old inflation picture of Booth, that the transition may not be complete at all. So if it is a too percolation of the bubbles will not happen. So too slow of S transition, that is restricting us to this parameter space. Okay, so just last slide. So Di-Higgs is pretty much only few points can be probed given this electric phase transition and strong gravitational wave production is there. And we can go back to the Higgs H2 decay to ZZ or WW, where sin theta 0.2 can be probed, but soon LHC Higgs signal strength is going to rule out this value of sin theta. So then it becomes tough with heavy Higgs decay to weak gauge bosons also. Okay, so that here I will stop, and this is the summary. You can read through. Okay, thank you.
Are there questions, comments?
What happens at the blind spot?
In terms of diagrams means
Like, is there a cancellation of the
branching ratio is too low.
No, but why? In terms of
I mean H2 going to H1, that just because of this so this couplings, you have we fix sin theta and Vs, and these couplings are such that
so the mixing angles become 0 for that particular.
Mixing angle is fine, but the cubic coupling. So what is happening is that there are two cubic couplings. One cubic coupling is giving you this electric phase transition, and the cubic coupling that is giving you the H2, H1 branching ratio. They are the two different ones.
Okay, so the second one has a combination of mixing angles, and that
Yeah.
can be 0 at some point.
Yeah. So that is, and accidentally, because Vs is allowed in such a small range, the non-resonant part is also very low.
Thank you.
So the region between sin theta 0.1 and 0.2 is something that is consistent still. Is that correct?
Sorry, Rohini, I could not hear you
No,
clearly.
can you go back to your last slide?
Yeah.
Maybe I missed something because I had stepped away for a few minutes. So can you just go to the last slide?
So this is
No, not this one. The last slide.
this one.
After this, the conclusion slide.
Yeah.
Yeah. So here what I was saying is that the region between sin theta 0.1 and 0.2, that seems to be the region that you would like, right?
Yeah, absolutely. I mean, 0.1 will also be tough. I mean, 0.15 is something where we have some access. So if you look at the ZZ, Higgs H2 decay to ZZ, so that is the best possible scenario. This is the green one is the 0.15. If you go further below, then even you are, so these lines are for 3 Attoburn inverse. Unless we improve our analysis at LHC significantly, even 0.1 would be tough.
Okay. Because up to 0.1, you have this possibility of Lisa and this thing, right? I mean, that you can.
Lisa, I think, yeah, I mean, 0.1 is certainly possible. I mean, so sin theta, I don't have the sin theta distribution. I mean, yeah, if sin theta, it can go pretty
But
low.
the model can be at least, because you have again a last line on your conclusions. So if you go back there, yeah, that the complementarity you are not able to establish for sin theta less than 0.1, but that is strictly due to the HL-LHC limitations.
Yeah, exactly,
correct?
exactly.
Okay. For the construction of your, other aspect of the Cosmo aspect is not affected by.
No, not at all.
Okay, thanks. Sorry, because I missed something in between. That's
fine. I mean, yeah.
Thanks.
Hi, I have a question regarding this electroweak baryon asymmetry generation process. So does it only depend on the velocity of the bubble wall, or like the tension of the bubble wall is also required for the amount of baryogenesis that you need? So
that's a very good question. So again, so it is a simplistic study in some sense that we just calculated the velocity profile from conservation of energy momentum tensor, and assuming that what we need for baryogenesis, this V plus, and given we know alpha from the microscopic model, we calculated VW. But that may not be the case. VW.
So you already know alpha.
Alpha we can calculate from just the Higgs potential.
Okay.
Yeah. However, VW also can be calculated from the microscopic physics, which is a very complicated calculation. And especially if you have extra gauge bosons in the model, it can create some kind of drag and change your VW. So all these effects you need to take into account in the next generation studies. And VW is not as free as we current studies are taking into account. But those are for a BSM model where you have extra degrees of freedom, or that those calculations are quite difficult. So at some point we need to do that.
Okay. Yes, I have another question.
Yeah.
It might be a naive question. Like, how is this process different from the case, for example, leptogenesis, which also requires Speleron process to convert it to baryogenesis?
Speleron you need because so we remain agnostic how this baryon number violation is happening.
Yeah.
So you can think of it is like some lepton number violation in the model, and which is by Speleron process you convert to baryon number violation. And in leptogenesis, the out of equilibrium conditions come from the heavy neutrino decay. There you don't need this first order phase transition. So that is how it different, leptogenesis and baryogenesis.
So the false vacua already has a
some lepton number violation, but the out of equilibrium condition was not created in the during that period.
Thank you.
Okay. So since we are already out of time, so let's thank the speaker again.